Okay, on to the second video of the week. In this video, we're going to focus on energy. And more specifically, by the end of this video, we'll learn about kinetic energy and potential energy. Like work, energy is a term that has many meanings and definitions, but in mechanics, energy is defined as the capacity to do work. There are many forms of energy. There's heat, light, sound, chemical, but in mechanics, we're concerned primarily with mechanical energy, which comes in two forms, comes as kinetic energy and potential energy. Kinetic energy is energy that's due to motion, whereas potential energy is energy that's due to position. A moving object has the capacity to do work because of its motion. This capacity is the kinetic energy of the object. And the kinetic energy of an object is affected by the mass and the velocity of the object itself. So mathematically, we define kinetic energy as half of the mass times the velocity squared. So KE here is kinetic energy, is half of the mass times velocity squared. And the units for kinetic energy are units of mass times velocity squared, which is actually the same or equivalent to Newton meters, which we learned in the last video is the same as 1 joule. So to determine the kinetic energy of an object, we need to know its mass and we need to know its velocity. And the unit of measurement for that is a joule. Okay, so for example, we want to know how much kinetic energy a baseball thrown at 35.8 meters per second has. So we know the baseball's mass, which is 145 grams or 0.145 kilograms, and we know the velocity at which the baseball is moving. So we plug all that into our kinetic energy equation, and we find out that the kinetic energy of the baseball is 92.9 joules. So determining the kinetic energy of an object is easier than determining the work that's done by a force because we can measure mass and velocity more easily than we can measure the force that's acting on an object. Okay, next we have potential energy. Potential energy is the energy that an object has due to its position. And there are two types of potential energy. There's gravitational potential energy, which is energy due to an object's position relative to the Earth. And there's strain energy, which is due to the deformation or the deformation of an object. There's also different kinds of examples of potential energy on the right here. So let's focus on gravitational potential energy first. The gravitational potential energy of an object is related to the object's weight and its elevation or its height above the ground or some reference point. So let's think of the following scenarios to make more sense of this. Imagine that you have a hammer and a nail and a block of wood. If you hold the hammer only an inch away from the nail and you drop the hammer onto the nail to try to hit it into the wood, it doesn't go very far. It does very little work on the nail because it has little potential energy. If you lift the hammer much higher above the nail and you let it swing down and strike the nail, it drives the nail much further. That's because the hammer does more work on the nail because it had greater potential energy. It was higher above the nail in that case. So mathematically, gravitational potential energy is defined as PE is equal to W for the weight times the height. And we know that the weight is equivalent to mass times gravity. So you can also think of potential energy as being equal to mass times gravity times the height. So the units of measurement for potential energy are units of force times units of length, right? We have force times a height, which is like a vertical length, which is Newton meters, and that's equivalent to joules. And that's the same for kinetic energy and for work and for potential energy. They're all the same unit. So to know an object's gravitational potential energy, we must know its weight and its height above the ground. For example, how much gravitational potential energy does a 700 Newton ski jumper have when taking off from the 90-meter jump? So you have the skier's weight and the height above the ground. And I encourage you to try to solve for the gravitational potential energy of the skier in this case. So potential energy is equal to weight times height. We plug in those values and we get potential energy of 63,000 joules. The other type of potential energy that we need to discuss is strain energy. So strain energy is energy that's due to the deformation of an object. So when a vaulting pole bends, strain energy is stored in the bent pole. So this is an example here of the pole vault being bent quite a bit, right? So there's a lot of potential energy that's stored in this deformation of the pole. In a similar way, when an archer draws their bow or when a diver deflects a diving board, strain energy is stored in that deformed bow or diving board. And the greater the deformation of the object, the greater the strain energy that's stored in the object. So the strain energy of an object is related to its stiffness, so its material properties, and its deformation. So mathematically, the strain energy of a material is defined as SE equals 1/2 of K delta X squared. So SE is strain energy. K is this stiffness or the spring constant of the material. And delta X is the change in length or the deformation of the object from its undeformed natural position. So just like all other measurements of energy, strain energy is also measured in joules. So if you think of a rubber band, for example, by stretching it, you've given the rubber band strain energy. And if you stretch it further, you increase the strain energy in the rubber band. The stiffer the object is, the greater the strain energy when it's deformed. Okay, so an example. How much strain energy is stored in a tendon that is stretched 5 millimeters if the stiffness of the tendon is 10,000 newtons per meter? So given this information, I invite you to pause the video and try to solve this now. If we know that the deformation or the delta X is 5 millimeters, we can convert that to 0.005 meters so that all of our units are in the same metrics. And we also know that the stiffness of the tendon, or the K value, is 10,000 newtons per meter. So we plug all that into our strain energy equation, and we find that the strain energy is 0.125 joules. So in human movement and in sports, energy is possessed by athletes and objects due to their motion, so kinetic energy, due to their position above the ground, which is gravitational potential energy, and their deformation, which is the strain energy. So in this case, strain energy would have come from the Achilles tendon here. Okay, so in this video, we learned about energy. We learned about kinetic energy and potential energy in the form of gravitational and strain energy. Stay tuned for one last video where we learn about the relationship between work and energy, and we also learn about power.